3.2 Polynomial functions in their graphs, day 1. Our learning goal has changed. Now, this acronym is students will be able to identify polynomials, find the end behavior, and use factoring to find zeros of polynomial functions. A polynomial function can be any function where you have your coefficients are real numbers and your exponents are non-negative integers. So those two things are really important. A constant function is in the form of f of x equals c, where c could be any number, any real number. Linear, we know, is the mx plus b. And then of course, you have your quadratics, which we just did. So these are examples of polynomial functions. The graphs of polynomial functions are smooth, continuous curves. So the corners are rounded, they're smooth, and there's no breaks in the graphs. So we'll write that just so you'll know about the graphs. Smooth, continuous curves. So example 1, it says determine which functions are polynomial functions. Those that are, state the degree. The degree is the highest exponent, so make sure that they are in order. And we call that standard form when they're in order from least to greatest. So looking at A, I notice all my coefficients are real numbers, so we got that in check. So we're looking for real numbers for the coefficients. And the exponents have to be non-negative integers. So I look at my exponents and they are non-negative. However, this is not in standard form, so I'm going to rewrite it. So this one's yes, and my degree is 4. And that's going to help us later. For B, now all my coefficients are real numbers. However, I have an exponent that's not an integer. 1/3 is not an integer. So B is not a polynomial. Example 2, identify which graphs are polynomial functions. Remember, we're looking for smooth, continuous curves. So A, this one checks out, yes. B, smooth, continuous curves. C has a break in the graph, so this is no because it's discontinuous. Discontinuous. So that means that there's a break in the graph. And D is no because of the sharp corners. See, those corners are really sharp. So we're going to learn about the leading coefficient test, which basically helps us to determine a polynomial's end behavior for the graph of a function to either the far left or the far right. So we call that end behavior. And there are 4 types of end behaviors. So I'll go over 4. So basically, if your leading coefficient is positive, I'm going to call it LC, is positive, and the degree is odd. Those are the 2 things you look at. Your 2 ends, and I always think about this as like a linear equation. On the far left, it's going to fall left and rise right. Okay? If your leading coefficient is negative, so think about a negative slope, and the degree is odd. So you know negative slopes go this way. And you're only looking at the ends. Your ends do the opposite. Now we're going to rise left and fall right. And then you have the even degrees. And remember, degree is your highest exponent. And you always have a positive or a negative leading coefficient. So if it is positive, you could think about a parabola. It's going to rise left and rise right. And if you have a graphing calculator, you can actually see this. And if your leading coefficient is negative, it's going to fall left and fall right. So the behavior for the even functions, they behave the same on both ends. The odd functions behave differently. Example 3, we're going to use the leading coefficient test to determine the end behavior of the graph. So according to the coefficient test, you look at the leading coefficient and the degree. Remember, the degree is the highest exponent. So I'm looking at the 11 and the 3. So the 11 is positive, and my degree is odd. So positive, odd. Remember, this is like a positive slope. So we're talking about the end behavior. What is going on the far left? What is going on the far right? So when you describe it, you say this graph will fall left and rise right. Okay? B. And notice I'm not looking at anything else. So for B, I'm looking at the 5 and the 4. So this is also a positive, but now my degree is even. Positive even, remember we think about the parabolas. On the parabola types of graphs, our 2 ends behave the same way. So they rise left and rise right. C, I'm looking at the -2 and the 3. This is what we call a negative odd. Negative odd, remember we think about a negative slope. Negative slopes behave by rising left and falling right. And then D, I'm looking at the -11 and the 4. This is what we call a negative even. Negative, and remember the evens, we think about the parabolas, but now they're facing upside down. They behave from the far left by falling left, and on the far right, they fall right. Okay, our final example, example 4, we're going to learn about finding the zeros, which is the same thing as x-intercepts. So if you see zeros, that's what they mean. So finding the zeros is like finding the x-intercepts. Then we're going to state the multiplicity for each zero. Multiplicity means how many times it occurs, which can be given by the exponent. And then 3, we're going to state whether the graph crosses the x-axis or touches the x-axis and turns around. So we call that a touch and turn. It only crosses the x-axis if the multiplicity is odd. And if the multiplicity is even, it does a touch and turn. All right, so looking at A, first thing you want to see is in factor form. So yes, it is. So you're going to take each factor, this factor and this factor, and you're going to set them equal to 0. And notice this factor occurs twice, so this multiplicity is 2. This factor occurred once, so this multiplicity is 1. So I'm going to set it equal to 0. So this 0 is -5, 0, with the multiplicity of 1. It only occurred one time. And since the multiplicity is odd, this will cross the x-axis. And if you have a graphing calculator, you can actually type it in so you can see how it looks. Okay, my second 0 was x equals -2. So it was -2, 0, with the multiplicity of 2. So since my multiplicity is even, it's going to touch and turn. Touch the x-axis and turn around. And those of you all who are visual, I'm going to actually show you what this means as far as graphing. I'm typing it in my graphing calculator. So at -5, 0, it would actually cross it. And then at -2, 0, it's going to do what we call touch and turn around. So that's how that graph will look. Okay, example B is not in factor form, so we have to actually factor it first before we can do anything. So I notice that all of these have an x in common, so I'm going to take out an x. And then I'll find two numbers that multiply to give you 4, that add to give you, multiply to give you 4, that add to give you 4. So that's 2 and 2. And I'm going to write it as x plus 2 squared. So I have x equals 0. So that multiplicity is 1. So that 0 is 0, 0. Then I have x plus 2 equals 0. This one has a multiplicity of 2. So that x equals -2. So that would be -2, 0. So since this multiplicity is 1, this is going to cross the x-axis. And that -2, 0 is going to touch and turn. Touch the x-axis and turn around. So it's kind of like the first graph I did. So it's going to do something like this. Oh, this is a positive odd. So I gotta come here, here, and back up. There we go. So it could touch and turn from coming from negative infinity as well. The last example we have to solve by grouping, or find the zeros by grouping. So I'm going to take out an x squared first, and that leaves x plus 5. And I'll take out a negative 9, and that leaves x plus 5. So I have x squared minus 9, x plus 5. I have to keep factoring, x plus 3, x minus 3, x plus 5 equals 0. I'm going to set each one equal to 0. And notice they all have a multiplicity of 1 because they all occur once. So that's negative 3, 0, 3, 0, negative 5, 0, all multiplicity of 1, all will cross the x-axis. So if this one, if you had your graphing calculator, they would cross, cross, and cross. So crossing means it goes right through the x-axis.